Good morning, everyone, and thank you for joining us for this week's Career Talk. My name is Faith Dukes, and I'm Director of Programs, K-12 programs here at Lawrence Berkeley National Laboratory here in Berkeley, California. You are attending a part of our career talks that we have over the summer that talks about a number of career pathways as well as research here at Berkeley Lab, as well as with researchers and experts around the country. For those of you who might need a reminder or might be new to us, we are Berkeley Lab, or Lawrence Berkeley National Laboratory. We are one of 17 Department of Energy national laboratories across the country, and you can see in front of you a list of the 17 national labs that are funded by the Department of Energy. We are lucky to have 4 national laboratories here in California. Berkeley Lab specifically is one of the largest research facilities in the country. It is home to 16 Nobel Prize winners, as well as it's been credited with the finding of 16 elements on the periodic table. And again, it's funded by the government, the Department of Energy, and is managed by the University of California. Here we have an extensive amount of STEM programs, especially for K-12 students. And this Career Talk series is a part of those programs. Over the course of the next few weeks, we are going to hear from some experts in different fields. Last week, we heard from a number of experts talking about their careers and the ways that internships, fellowships, and experiences contributed to their success. Today, we are going to talk about machine learning for good and artificial intelligence. Our 2 speakers today specifically focus on healthcare as well as material science. So while machine learning and artificial intelligence are broad spectrums of the science and technology space, we are specifically focusing on these 2 areas of their research today. We look forward to talking with them and answering your questions in the chat box. Today's session will start off with our speakers giving 2 introductions of their own work, and then we'll open it up for some moderated questions as well as questions from the audience. So with that, I'd like to welcome our first speaker for the day, Professor Adam Yala from University of California, Berkeley, who will talk to us about his research. So Adam, if you'd like to join us, thank you for joining us today.
Hi, everyone. Thank you for having me.
All right, so Adam, I'll let you go ahead and start to share your screen and speak to us about your work you're doing with machine learning.
Sounds great. 1 second. Cool. Okay. Well, I'm very excited to share some of my research with you today and tell you a little bit about how I got here. So without further ado, let me tell you about a central observation driving a lot of my research. So across multiple diseases like breast cancer or lung cancer, we know that the earlier you catch it, the better. This is what I'm showing you here on the left-hand side and right-hand side is overall survival plots. So if you catch cancer in really early stages in breast cancer, survival is like 99%, and sometimes the treatment pathways are not too severe. The later you catch it, the worse the outcomes, meaning both lower survival, but for the survivors, you also have more intense surgeries, more intense chemotherapies, and just a way lower quality of life. And this is true in breast cancer and many others. So a key question of my research is, well, how do you catch cancer systemically earlier? And I'm going to show you kind of a very simple 2-step plan. And I'm going to argue that both of these steps are actually core machine learning and AI problems. The first problem is foresight. If you want to catch cancer earlier, you need to know who's going to get it, right? That's normally called in our community predicting cancer risk. And on the right-hand side, once you have foresight, you need to do something about it, right? You need to change how we think about who gets screened for cancer and when, so that systemically everything is caught at the earliest possible stage. So I'm going to briefly talk about the first part of that picture, but both of these things are kind of areas of really exciting machine learning work. So let's first talk about that first picture, how we can get foresight about who's going to get cancer in the near future. Now, I want to emphasize, it's not really the picture on the right. It's not looking at year 5 and saying, oh, the tumor's right there, draw me the box. It's a much harder problem. It's looking at the picture on the left when there's no cancer that radiologists can see. There's nothing for them to biopsy. But how can you learn from that point that this person will develop cancer soon, and so you should do something about it? And that's been a focus of a lot of our papers, and so I've kind of listed some citations here. So I want to note this is not a new idea, right? People thought about this since like the 1980s, but the classical way we've thought about this for decades and decades, this is true in cancer, but also like in the rest of medicine, is we use expert knowledge. We say like, okay, well, age matters. The older you are, the more likely you have to get cancer. Family history matters. There's some like other markers we know about that matter, like something called breast density. But in general, we know the world. We're gonna basically assign to say, here are the couple of variables that matter. We're gonna ask maybe like 10 questions from the patient. Then we're gonna use that pre-specified expert knowledge to understand who's gonna get the disease. And the metrics here I'm showing you is just AUC, like 50 is random, 100 is perfect. So like 60 is kind of mediocre. And despite decades of effort, we've kind of been stuck in this kind of like low 60 mark. And so one of the kind of the first key departures we took in this space and how to think through, well, how do you make this better, is instead of relying on expert knowledge, let's try to learn something directly from the data. So prior methods already looked at the images. They already said, we have these images, we're going to say like, how wide are they? Either they're category 1, fatty, category 2, scattered, and they're just kind of like, we're manually extracting what matters from the image. Instead of that, one of the things we looked at is, well, what if you look at all the hundreds of millions of pixels in the image directly, and then treat it as an AI problem to learn who's going to get cancer. So in blue, someone gets cancer in the year 3, someone gets not cancer at all, someone in year 5. And now our job as AI developers is, how do you then build models that can learn this function directly from the super high resolution pixels? But now it's the AI's job to find the correct hypothesis. And without belaboring some technical details, the kind of like big picture here is that compared to the kind of clinical state of the art, which has like super detailed questions, you get a really huge margin of improvement in performance. So this is showing you kind of the MGH set, which is a hospital in Boston on the left. And the right-hand side, I'm showing you that it's one thing to say like it works in one place, maybe it's a fluke. So we worked really hard to kind of get global validation studies with partners all over the world, and every place ranging from Brazil to Taiwan to Sweden and Israel, across most places in the US, we see the model gets the exact same performance. So it works and works reliably. Now I'm going to briefly say like, what does this mean and like what's the kind of clinical implication? There's actually 2 ongoing clinical trials running right now. Both of them kind of come down to the same idea of, if you know who's going to get the disease, you can give them you can change how they're screened to give them more sensitive type of test, so that the cancer gets caught at an even smaller stage. So we can think we do this roughly 2x better than prior art. We can kind of talk more about that later. And I want to briefly mention, this is not a uniquely kind of breast cancer picture. We have very similar work on lung cancer. We're hoping to replicate this across many other disease systems. So here on the right-hand side, I'm just showing you they're the expert knowledge, smoking history, but if you look at the image directly, you can do way better than that. And there's a lot it's a very repeatable story. And similar to there, we show their works across external validation, and that it's really a broad and generalizable phenomenon. And one last thing before I kind of close the research part of my little introduction, I want to show you what it looks like. So on the right-hand side, I'm showing you some pictures of when the cancer was caught. And then on the left-hand side, I'm showing you pictures of when it was called high risk by the model 3 years in advance. In each of these cases, it's not something that the radiologists can just kind of say is cancerous today. So really what the modeling is doing is they're discovering new things the radiologists don't know and don't understand. I think that's something that's really exciting about the space today. So that's kind of the first half of the picture. I'm going to briefly kind of show the citation that there is a whole other line of work of how, if you have this information, how you can kind of rethink how we even think about how to screen people. You can kind of design nearly game-like formulations where you can learn to screen so that you can kind of personalize the regime by the person. Okay, so that closes the research bit of the talk. I don't want to go on for that for too long. I'm going to give you a little bit of introduction about myself. So hi, I'm Adam. I immigrated from Algeria, so I moved to the States around 2005, where I learned English and lots of other things. I did all my training at MIT. So I did my undergrad there in computer science, my master's there, and eventually my PhD. I graduated about a year ago before starting my role here. And in general, I really kind of, I've always wanted to do research, but I didn't know research was what I was looking for. So I kind of stumbled through different computer science type ideas. I did some software engineering jobs from 2012 to 2015 in my undergrad through internships. And each instance, I was deeply unsatisfied with feeling like I was solving the same problem over and over again. Like nothing felt like it was at the edge of what was like trying as hard as I possibly could. And in 2015, I cold emailed a bunch of faculty. One of them responded. I joined that lab, and that's how I got here. And overall, my goal as a faculty member at UC Berkeley and UCSF is to develop algorithms to reshape how we think about cancer screening, diagnostics, and treatments, ranging from this kind of like public health picture down to some level of like drug discovery. and I'm excited to chat. Yeah.
Thanks, Adam, and thanks for giving us such a great introduction to you and to your work. I am going to ask our next speaker to come on line, and Adam, you're going to turn off your camera, and we're going to switch to Yan Zhang, who is a research scientist here at Lawrence Berkeley National Laboratory doing machine learning work, specifically in material science. So Yan, I'll switch it over to you and allow you to introduce yourself.
You're still muted.
Hi.
There we go.
Can you see my slides?
Yes, they look
Awesome.
great.
Thank you for the introduction. Hi, everybody. Good morning. My name is Yan Zhang. I'm currently a materials staff scientist here at Lawrence Berkeley National Lab. I work in a lab that we recently built and which is operational right now, as you can see part of the picture here, which is powered by AI and robots for doing materials research. I will start with introducing a little bit about my career trajectory. I have been in general in the chemical and materials engineering field, where I started doing research programs and research projects when I was doing my master's degree in China, where my research topic was very different from what I'm doing right now. So it's basically to design sustainable industrial chemical processes for this large scale production. Then I moved to Canada to pursue a PhD in materials engineering, where I used some of the chemical engineering tools, but instead of focusing on the industrial process, I now then developing advanced battery materials for electric vehicles and electronic devices, which lead all the way to, after my PhD, I moved here to California to do research in material science and specifically to start building a lab that can use AI and robotics as tools to really like power and accelerate the speed that we can do materials research. My goal and my passion is to, along with other team members, to develop better and innovative materials and to power a greener future. This can be some renewable energy, such as solar energy, wind energy, and it can also include battery systems like lithium-ion batteries that the electric vehicles are using right now. And all of these technologies requires a higher efficiency and also better sustainability, which fundamentally relies on the materials that we put into this different technologies that either generate energy or store the energy. So making new materials is not an easy task, though we have been dreaming of something like this in Iron Man's scene, where you see Tony Stark in his workshop. He can basically choose the element from this periodical table, and he can sort of vision which element will be good to be combined with other things to make maybe the best armor or something. Well, here we wanted to build a lab that basically do the same thing with a different goal. We want to make the best battery materials and maybe other materials, etc. So here in this picture, it was back to this February this year, where we just sort of started the launching of this lab, where you see one robot arm picking up one sample that's a crucible from this platform. So here I have a bunch of videos that to show you how this lab is in motion. But before that, I can sort of give you some brief ideas how we use AI and the robots as tools. Basically, we use AI to design experiments for us. For example, what kind of ingredients we want to put together, and what's the temperature we want to sort of heat up this ingredient to trigger some chemical reactions. And then this command will be sent to a robot or several robots to do the experiment, moving things around or operate an oven or something like that. And after all the experiments are done, then we again use AI tools or machine learning tools to process and analyze the results and to give us some outcome that we as human researcher can understand. And also another AI can understand, so that it can make further predictions of what to do next to reach the final target or make the best dish, for example. So here we have 3 videos, and they are different steps in this whole synthesis procedure to make a new material. So the first step is to dispense and mix powder ingredients together, pretty much like what you will make, for example, mix some sugars with a coffee powder or something like that. So here is the number 1 robot arm, who is very busy at picking things up. And here is a balance that's to measure very precisely how much amount of the virus ingredients that have been dosed to this container. And here is another step that is to pick up from this machine that has been doing the mixing step. And here is a hot plate to heat this vessel up. So this step is done, and another robot arm is waiting outside this enclosure and pick up the sample that has been prepared and sending it to one of the furnaces or oven that it has been assigned to. We also batching several samples together so we can have a higher throughput of our experiment, and we can make full use of this furnace, for example. So then the baking is going to get started, and it can last for 1 hour to even 24 hours, depending on how long we want to do the cooking. And after all this is done, we need another AI to understand what is the result, right? What is the product that we get from this whole processes? So here is another robot arm trying to process this sample that has been made from the furnace. And it can get quite busy with different tasks, picking things up, different kind of containers. And here is to dispense some of the product to the sample holder, which will be sent to the analytical instrument later on to do the analysis. And each robot arm is equipped with its own camera, so it can use computer vision to see, visualize what is a sample, what's the quantity and the quality out there, so that we can get a better sense of the quality of the experiment. So this is pretty much the video of how this lab works. We call this A lab, so it's like autonomous lab or AI powered lab. So to finish up of my introduction, I want to summarize a little bit like what are the roles of AI and robots in the research like this, right? We have the automation part where we use robot arms or other types of robots to do sample processing, handling, or to automate a certain hardware, like the door can open automatically, for example. And then we use machine learning tools to process the data, to collect and then process and analyze the data to give us information, something like this. For example, manganese oxide is one of the chemical compound. And this information is given by the machine learning model that has processing this spectrum, that if we just look at this spectrum, we get no information, right? Now we are on our way to all the way transform from automation to autonomy, which will require more advanced AI to make better prediction and to make decisions for based on reasoning and based on the previous achieved data. And in the near future, we also hope to have AI to help us to generate a hypothesis, like even to ask questions, what should be done next in research, something like that. So this is pretty much what I want to share today, and I'm happy to answer any questions later on. Thanks.
Great. Thanks to our speakers for giving us such great introductions. I'm going to have you both turn on your cameras again so that we can start our discussion. And I will say to the students in the audience and to our attendees, you are more than welcome to ask questions that we'll pull from the chat as well. I wanted to start off by asking actually a question that we didn't talk about just yet. But the fact that you all have to be working with so many people in order to, do your research, everyone from doctors at the hospital who are actually interacting with patients to, engineers and people who are building the robots, designing your laboratory. So I'd like you both to just speak to, one, how many people are you collaborating with, and what do those people, end up, what perspectives do they need, and do you need in order to work with them? Adam, if you want to go ahead and start.
Sure, yeah. So I think a large challenge this is true in science in general, isn't just like build the model well and like solve this question well. It's more, how do you pick questions? And for that, collaboration is like totally critical, because I'm not a clinician. I'm not actually treating cancer patients. I don't understand all of the ways that data is getting generated and the constraints that they're facing. And at the same time, it's not just like the clinician can tell me, oh, here's exactly what we want, because they don't have the computational framing to like understand ways it could be solved and things that feel impossible. Like an outside perspective can be very useful, because then you can kind of question things that are otherwise taken for granted. And so the best way to deal with that, to like get the best of like being on the outside and the innovative that gets you, but also like not solving useless things that like people don't care about, is by having like really close collaborators that like you like deeply understand and talk with all the time, to make sure that you're solving the right questions. So for every one of my projects, and I have too many for my own good, but across every disease area, I have different clinical collaborators that I both work with to make sure we're asking the question the right way, that once it works, we have a pathway to bring it to impact. Because let's say I have a new model to do X. Who cares? Like, I want a model to like not only does X, but it actually runs through clinical trials and actually helps real people. And all of that translational journey, like I'm part of that journey, right? Like the tool being developed and stuff is important. And like, but the next trial bits and all this pathway to impact is a story with many hands. And it's really important to kind of build that team and that coalition from the beginning.
Awesome. Ian, do you want to also jump in on the engineering side and material science side?
Thank you so much for starting with this question. I think it's a great question. So especially in the project, like this autonomous lab project, teamwork is really, really essential, because as you can imagine, like we need, me, myself, I sometimes consider myself as a materials or chemical engineer, where I know like kind of well about batteries, materials, those kind of aspects, but I knew nothing about robots. I knew nothing about machine learning like 3 years ago when I started in this project. So we needed people from different areas, and believe me or not, like many of them, they also didn't have any background in machine learning or computer science as well, but people sort of pick up what's the areas they are interested in, and they might have strength and sort of they want to put effort to learn fast. So we brought a team of people together. So in total, 10 people in this team to start to sort of, in the beginning, is to sort of to imagine about what kind of lab we want to build. Well, I took kind of the leading role to sort of define the scope of what we want the robots to do. And then we sort of divided to different tasks, like what kind of machine learning models we may need. We may like borrow from other people, what other people have developed, right? And then make improvement from that. And we also need people who have more sort of hands-on experiences of, let's say, install or put actuator like to open the door or something like that. Or some students may be more interested in like train a robot arm to move from task to task. So we all sort of come together and learn together and pick up a certain task. And many times we have a lot of sort of overlapping, I would say, like aspects, like we need to share with other people, right? So the person who is interested in training the robot arm also need to sort of collaborate closely with another person who sort of knows better what kind of movement we hope the robots to do later on, something like that. So in the end, like everybody knows a little bit like well about his or her own stuff, and also know a little bit about other stuff. Like I know a little bit about machine learning. I'm not a machine learning person, but because of we are involved in this so like collaborative project, we are exposed to a lot of like information and technologies, which is really like great and awesome.
So I would go back to machine learning is, at least in terms of terminology, new to us as a general population that we're hearing more, but how would you yourselves define machine learning, and why is it so important for us to learn about it and to know about it, especially how it might impact our lives in the future? For either of you, who would like to start?
Sure. I mean, I would say machine learning is the science, the discipline of extracting meaning from data, or like extracting patterns from data more generally. And I think there is like the first kind of application you can think of, and where you really see most of the kind of commercial and like, real life kind of adaptation of that, is just automating and helping in settings we really know how they work. Like you can kind of like try to build an autopilot system for cars and say like, okay, this is a person. You can do that. That pattern exists, right? Like you can like look at an image and say that's a person or that's a stop sign. So a lot of progress you've seen historically, machine learning has been, how do we kind of bake into computers things that we know about the world? But more and more, a lot of the frontier has been, how do we use the same kind of technology to do things we don't know how to do, and make that the kind of frontier of knowledge. So like, for example, in the things that I presented in my research, like people can't look by eye and say this person's going to get cancer. We just can't. We're really bad at it. People can look at a protein and say how it's going to fold. Also really bad at that. But their signal exists in the data. And so there's a lot of work of like, how do you not only automate understanding of things that we know how to do for, to make things more convenient or reduce costs or whatever, but also how to automate things that we don't know how to do and use it for discovery, which I think is super exciting. I think it's like the frontier, and it touches every science. And I think it's that's what I'm stoked about.
Yeah, so for my research area, I think what we really find machine learning very powerful and useful for us is its ability to sort of make predictions based on the data, previous data. So, but there are different aspects or different sort of level of difficulties or challenges in when we apply machine learning to different fields or different tasks. Like in our case, I can sort of give examples of like 2 examples. Depending on how difficult it is. Like the first level, I think, is to kind of process the data, like process a spectrum of something, and then output a meaningful things like, oh, what's the chemical compound when we look at that spectrum or those peaks. Well, human being can also do that. We are good at it, but it takes us sometimes 2 hours to process one single spectrum, whereas once we have a well-trained machine learning model, that's just 1 second thing. So that's the powerful things. On the other hand, the second example is to make predictions more general kind of for the decision making. Like once we have all different kind of results, like 10 sets or even 1,000 sets of example of results, what we should do next to get to the success. Because most of the times when we do like chemical experiment, we have a lot of sort of failed results or something like that. So what machine learning or other kind of AI tools are good at or is getting better at is to make predictions on all those kind of different types of data, and at least to give us a larger probability to get to the success faster.
Yeah, you kind of just tapped into a question that someone asked and said, what are the areas of your job that are more challenging than others? It might be those experiments, but there might be something else. And Adam, I'll ask you that same question after Yen. Just what's the most challenging part of your research, or what's most challenging out of all of the things that you do?
I think the most challenging part is actually to frame a good question that will eventually lead to a scientific discovery. To be more specific, for our case, our goal is to design and develop materials that are technologically like important. So at this point, we still like as human researchers, we still have to put a lot of our domain knowledge and a lot of work on based on previous work, sort of to define a certain question or problem for the AI to solve. So I think a more challenging and more for a future direction is to have an AI that can ask questions and sort of frame or change questions by itself, sort of, which will eventually lead to the discovery.
And Adam, your most challenging portion of your day out of the many projects that you're doing?
Yeah, I'll answer that in two parts because like I mean I recently went through this kind of like phase shift in my career because before I was a grad student and I was like doing individual contributor work. I was doing what I would call real work and that there's problems I was trying to solve as a person. Whereas now I'm like as a professor I have PhD students that I mentor and my responsibilities are much broader and the challenges are very, very different. So like as a grad student, to me the key challenge was uh how to stay creative in the face of just constant nothing working all the time for like a year in a row, which is a different kind of challenge than it is like when you have a class project, like you know it's going to work. Like it's a class project, like the thing is possible. You just need to figure out how to do it. And that's a different kind of hard than when it's not sure if it should work. Like maybe the idea is just wrong. But as soon as you believe that it's wrong, it's definitely never going to work. Right. Like so there's a little bit of like you have to stay optimistic and stay creative and really give it your best shot in the face of constant setback. And I think that kind of like constant optimism is kind of hard because when do you give up on an idea because it really is just bad and try the next one versus when do you need to try a little bit harder in that kind of uncertainty and staying really optimistic and happy in that kind of chaos. I think is like kind of one of the core challenges of being a PhD student and how to stay focused in that setup. As a faculty member, it's more now I have mentoring many students to do different projects and the challenges are kind of different because now I'm not thinking about how to solve those individual problems. It's how do I help them grow faster? And I have that responsibility. I have to teach. I have to like fundraise to like basically win grants to support them. And the hardest part of my job now is how do I manage myself being pulled in a million different directions while making sure nothing falls on the ground. All of those individual parts are hard, but if I do any one of them too much, everything else falls on the ground. Everything goes really bad. So like the beauty of being an individual contributor is you get to focus, and focus is so beautiful. You learn so much, and everything like builds the next knowledge. Whereas when you can't focus, and that's your prime job description is to not focus and to do a million things. That's how to be effective in that regime is its own new challenge that I wrestle with all the time.
All right. I think you both have hit on those, answering or finding the right question to ask. Is it significant to your collaborators? We also talk about in our programs, deciding if something is just difficult and you need more help, or if it's just not for you. Whereas you're saying, is this a difficult problem that needs some different perspectives, or is it something that's just not the best answer or route to go down? So those are all helpful in all of our journeys. Someone asked, speaking on kind of, Adam, you're touching on this a little bit, what is your weekly or day-to-day life involve as a professor? And then Yan, as a scientist, what is your daily, weekly overall outlook, for your calendar kind of look like?
Yeah, so about 2 days a week, I'm literally on Zoom or in meetings from like 9 a.m. to 6 p.m. And those are like times I'm meeting with my students all day long. And I have just back-to-back meetings with different students. And it's honestly loads of fun because every student's a different project. They do something very different. And then it's just diving deep into like the problems they're wrestling with and trying to kind of both go through what those results mean, what experiments to try next, and also trying to guide their growth. And like seeing students get better and like compound gains is just like exhilarating. And it's because every project is so different. Like it's not like you're in one 9-hour meeting. It's like everything is like you refresh your mind every time, and that's loads of fun. 3 days a week is when I try to do what I would call, let's say, more real work, which is what I mean. Like I'm either writing grants, I'm trying to like come up with the next generation of idea to then fundraise for so I can recruit more students or get data for the things. Basically, I do the work of like how do I pull things together to support my existing team and to grow the team more generally. And then a chunk of the time is also designing curriculum and teaching. So it's I'm a little bit all over the place all the time, and it's part of the chaos of my life. I also I'll indicate that like it's not just like work. It's important to like do other stuff to like be sustainable. Like because it's not about being productive for a week. If you're productive for a week, you can do all kinds of compromises. We need to be productive for like a career, right? Like for a long time. And for a 30-year thing, you're not gonna like not sleep. Like none of that stuff scales. So I spend a huge amount of time like climbing and doing. I'm actually in Tahoe right now in my camper van. It's awesome. And like yesterday I was on Zoom from like 9 to 6, and then I went out into the mountains and just climbed for 4 hours. It was great. And so I do a lot of that. And I have a very fluffy dog. It also helps. Yeah.
Yeah, and how about you? What's your day look like as a scientist?
Oh, I don't have a dog, but I have two cats. So I'm in kind of in a transition from like a trainee into a trainer. So I now kind of independent, not half, kind of semi-independent. I don't have my own students, but I do like train and mentor students for my supervisor. I still have a supervisor above me, which means that I sometimes still sort of to work for the larger team. And I also have my sort of own small team that I work more sort of closely with. So my day to day, well, each day is really different to another day, depending on what the deadlines most of times, like what's on the task list. Like I also write grant for myself and for the bigger team, and I write papers and sort of have discussions, more or less kind of casual-ish with students. So my style is more or less like I have this, for example, 10 a.m. to 1 p.m. open. So if anyone needs my help, just sort of you can just tell me in advance and we can book a time and we can chat, sort of to see if I can help them and students to solve any problem or make a progress. Other than that, I try to keep at least 1 to 2 hours of time that I focus on writing. Because at this stage, like I feel like a lot of tasks is related to writing. So writing and reasoning together is really like essential. And out of that, it's continuous sort of thinking about the challenges and what to do next and how to solve problems in a certain project. Like for the autonomous lab which is already sort of operational right now, there are still many problems or many parts that we can sort of upgrade, right? So many times I would wake up sort of thinking, sometimes dreaming, and then waking up like thinking about those things, like what can we do as a team sort of to solve that problem? Or is that problem solvable? What can we do next? So thinking is kind of a lot of it's a lot of time, and which is also great. I kind of enjoying it. So other than that, I don't have that many Zoom meetings since last year, I think, which I don't know. I kind of more or less prefer in-person meetings. I find it more sort of efficient, but sometimes it's just not an option, right? But anyways, I enjoy sort of interacting with people by talking to them rather than email. So I still, again, like spend a lot of time on emailing people or replying, sort of those kind of things. Other than that, I try to keep kind of a relatively healthy sort of schedule. So I do exercise, like strength training. I was doing climbing like Adam, for sure not an expert, but then I sort of hurt myself a little bit and then I had to sort of pause. So for that kind of thing, we really sort of need to be cautious when we get started with and equip us with the right skills. But I feel like doing exercise in general or outdoor or indoor activities are really sort of help for us to either like to write into something or to think something. So yeah.
Awesome. Great for trying to get some work-life balance in there. And I think we even talked about last week, communication. It's always important. If anybody's going to care about your work or if anybody's going to collaborate with you, you must be a good communicator. And I don't think we often talk about how much writing comes into being a scientist, being a researcher. You really do have to write quite a bit. And we got a lot of questions in here, so I'm going to try to get through them as quickly as possible or as many as possible before the end of our hour. What do you love about AI? Why this subfield of research and not others that have been explored? And a little bit of twist for you, Adam, is, was it difficult to go from a software background to this background that you have now that's healthcare centered? Is this a common trajectory? So yeah, and just what do you like about AI and why this subfield of research and not others? And then Adam, to you, but also, is it common to go from a software engineer into, say, more of a health focused career?
Okay. So, well, I like AI and I like many other tools. So I guess I won't say like I absolutely sort of prioritize AI, but AI is kind of now becomes essential when we deal with a lot of data and when we want to make like fast decisions or sort of when we want to move forward from one thing to the other really fast, sort of, and also like sort of existing the power, the capability of each individual researcher or something like that. And sometimes I also find AI kind of a tool that connecting people, even collecting like human together so that we can communicate better. Like I have some like colleagues who are better at computer science or machine learning algorithms in general. And now, because we can sort of really apply those tools to do experiment, so I find myself like understand better what they are doing, and they understand better what I'm doing as a material scientist. So, and in the end, we all like sort of contribute all these things to a real project, then like a lab in our case that can really start like doing a lot of things by combining different kind of tools, where again, like AI is kind of the essential part to move data around and to process data and make predictions.
Adam, why AI, and then do many people take a change in their trajectory of work?
Yeah, so the reason I wanted to work in AI is kind of the same reason I got into computer science in the first place. I wanted to basically to be able to work on anything. And to me, computer science was something that was so cross-cutting. And modern machine learning is the same way. Like I have projects in which I'm looking at like things that are very clinical. Like how do you think about like public health, how to organize screening programs? And the methods that I think about there are basically the same family of methods as my friends who work on like protein design. And as my friends that work on like more like material, like how do you think about arranging novel structures? And it's the same thing as talks about people who work more like in economics or like in like diagnostics. It's like it's a skill set that is so cross-cutting that like you can really bounce around a lot during your career. When I actually started, I didn't start off working on health. I started working on language. Like my first projects were like information extraction, instruction following. Think of like ChatGPT style stuff, except like way older, not nearly as good. Like that's how I got started. And then like opportunities came up in the cancer domain, and I was like, oh, I want to work on that next. And the skills just immediately transfer. And now like today I have products ranging from like drugs to diagnostics to public health to like some fintech stuff of like in rural India, like, and all of that is the exact same methods. And so you can just really bounce around and it's loads of fun. And like my PhD advisor is someone who every 5 years just like totally changes the fields in the lab. Like when I joined, it was an NLP group. Like we worked on like translation and decipherment and like summarization, all this kind of like language tasks. When I started, I built up our cancer direction, did a lot of imaging stuff. Some other people worked on a bunch of like small molecule antibiotic discovery. None of that is what they're doing anymore. Now they're doing like protein design and docking and some quantum stuff. Like, so the ability to like always work on new stuff and stay excited is something to me is like super beautiful. I would say transitioning into the field, like it's not that hard. I mean, I would say like it's a long game. Or like, I went 3 years on a very like engineering type track, and the engineering skills directly translate because like modern AI is like very software heavy, and it's like you need to write good code to make that happen. But I don't think like at any point like it's too late to learn new skills. Like the thing that are like, as long as you like, the most important thing is like your mindset to like face constant things feeling really hard. Like the learning curve can be pretty steep in the beginning, but as long as you try, it's a matter of time, right? Like it's not magic. So I don't think that that transition is very uncommon. It's kind of hard to have access like from high school, and so either way, some people transition from somewhere, and it's basically never too late to transition. And if someone wants to work on it, it's just going to take some time to learn. But it's a long game. It's not like you're trying to do this for a year. You're trying to do it for like many years. So if you spend a year or 2 years or 3 years learning, it's like whatever scheme of things.
Some great answers to those questions. Keeping going, we have a question about, or we're going to put two together. One, how do you frame a question for starting a research project? And then when do you know you're at a point where you can share the work that or your conclusions or your evidence that's come from that work? So how do you frame, and then when do you get to the point where you say, I think I'm ready to share this out with the rest of the world? Yen, I'll start with you.
Sure. Yeah, framing a question, it's kind of also like a long process. It really depending on the scope of the research. which is more or less sort of defined, right? Or the basic, like the general goal of the research. Like again, in my case, I know that my goal is to design and develop a material that is better than what we have right now to power electric vehicles. So we sort of already have something, sort of some constraint or boundary conditions in mind. What kind of material, what kind of elements that when they put together, they will perform good. Perform good means you can drive your vehicle for longer distance, for example, and also have better safety. So we already have that kind of scope in mind, and then the question can be as simple as element A and B, when we put them together, are they gonna sort of react and work good with each other? So that can be a question. And then we can do sort of research, sort of design experiment. It can be as simple as, okay, let's make A and B together, and then we do a bunch of tests to test their performance in a battery, something like that. So at which stage we, I think the next question is kind of at which stage we can sort of share or make a conclusion, something like that. So in some research, in some type of research that can be very straightforward, like again, for the battery research, the conclusion or the way that we sort of to judge a conclusion, judge a result is easy. We just see, okay, does this battery like function good? What's the distance it can provide, right? So once we have that number, we already have a conclusion. And the sharing is a continuous process. So usually when we work in a research team, we have a lot of like discussions in the team, and we have meetings, group meetings to sort of present our results from the very beginning to the end. So everything is kind of shared with other people so that we can also get feedback from other colleagues who may have some other insight or have other sort of feedback about what we have. But for some research, the conclusion may be more difficult, like for the autonomous lab, which we ask AI to explore materials or something like that. We have to sort of accumulate more and more sort of data and knowledge until we can really make a conclusion like, is this AI performing better than us, something like that. So sometimes it's kind of like an open conclusion. We don't really define what is good, what is bad, or what is better, something like that.
Great. Thanks, Yen. Adam, how do you formulate a research question, and at what point do you think this is ready to share?
Yeah, so question formulation, I don't really I formulate them as, let's say, AI questions. I always try to think like, if this thing will be helpful for a meaningful health problem in general. And then I will discuss that a lot with my different clinical colleagues to kind of try to what would be, if it existed, useful. And then once I have here is the target in mind, then what are AI ways to help solve that problem? What can I do from my perspective to help bridge that gap? And viewed that way, it's often not that hard to say here's things that if they existed would be very meaningful in the clinical domain. Lots of things are just not very good and have lots of room to improve. Then there's kind of a filtering that is okay, now what do I think are well positioned to solve today given current resources? And how does that what's the right fit given our current skill sets, and what I think is going to be most let's say highest impact for this next year of effort. In terms of when to share results, I'm comfortable sharing interim results whenever. There's no real secrecy there. It's more of I only it's when to write the paper is when you have something. There's two constraints. One is is the advance big enough that you even want to bother writing? Writing's a lot of work, right? It's a lot of work to put together a good paper, run it through the qualification process, do all the kind of press around it. It's a huge amount of work. Do you want to make sure you have something quite meaningful to say? And that the work is significant enough that you're ready to fight for it and try to change how a field thinks about something. So there's kind of a boundary of is this cool enough to justify the effort? And the second part, even if it is cool enough, will it get way better in a week? Because once again, it's a lot of work. So if I can wait a week and that's even better, then I'm going to wait a week. I want to basically make sure we've done our best and the thing is in kind of the best shape, and there are not any immediate new gains are going to come up in the immediate future. and it passes the bar of being significant enough that it's a big deal, and that I think it's worth spending a lot of effort to communicate to the rest of the community. But if anyone ever asks about interim results, like how are things going now, I'll tell them it's fine. It's not going to be as interesting. It's like, ran 12 experiments yesterday. None of them worked. That's okay.
That's when you go rock climbing, right? But talking about that and talking about the work, just quick yes or no, someone asked, would you say it's more complex to actually do the research or write the paper? Which one would you say is the hardest one, or maybe they're equal, just both different thoughts and perspectives?
Maybe I can start. I think they are really they're always kind of intertwined. They're always together. Like writing a paper, or even like start planning research. How can I frame this? Like in a paper, there is like the general structure of the paper, right? And there is the main message you want to put in the paper. So that all kind of related to the research that you have planned in the beginning. Although like it's not always like what you have done, you will report whatever, like everything you have done in your research, like Adam explained. We want to report what's meaningful for other people, for the broader field as well. So sometimes a lot of data or research results that might not be even like published later on. But in general, I think these two things are always together. And it's like, or say like writing a paper is part of doing research, because eventually we want to share with other people from the same field or from other fields.
Yeah, I would also add that they're deeply intertwined, but I think like the act of building new stuff definitely takes way more time than the paper, right? Like something might be like a year of work, and then maybe you spend like 3 weeks polishing the writing, and maybe like cumulatively maybe a month of like peer review stuff. That being said, like they really are like codependent. If you have like phenomenal results and it's written like terribly, then no one's gonna care. It's like it never happened. Like bad writing can just destroy a paper, even if the fundamental ideas are really, really compelling and really important. And so there's no amount of like fantastic results that will save a paper from bad writing. And similarly, if you have bad results, no amount of writing will save you. There's like, if it doesn't work, like it's not just about like, does it get in this time? Like, because the true value isn't whether or not how people think about it today. It's as the years go by, was it truly useful? Did it really move the community? And so for that to happen, like the result has to be truly good for it to be useful to others. But you're only going to do that if you convince them. So it's codependent. Different challenges though. It's communication is very important.
Yeah, we'll continue to say that. And the right is important, communication is important. I think that's a theme for everything. I want to get into, you have a couple of questions that people have asked about our, coexistence with AI as we're bringing in different robotics, we're bringing in different platforms that are taking over what we may think as human jobs or human related jobs, or that might take away a job from someone else, or might take away specific roles that people have. So how do you think about the coexistence of AI and human life, and how can we, utilize them in order to work, better, instead of thinking about them as, this is taking over a job of some way? So Adam, if you want to start back, like, how do we think about our coexistence with AI?
Yeah, I really think of it as we're expanding the reach of what a human can do, like substantially over and over again. Like I don't think it's that profoundly different than, let's say, the invention of the car. Before, like if you couldn't travel this distance before, they can travel way bigger distances, which gives you bigger reach. And it's true for kind of every tool that we think of. Like the tools that I've been working on, like all this like personalized screening stuff, we just can't do it today. And so there's no job for it. We just can't do it. We don't have the capacity to do it at all. If you build good enough AI to do it, then you're just helping more people survive longer. And that's just a new function that now we can do as a society. And I think many things that way are the kind of value chain. Like, for example, there was a time in which you can only really get any translation by paying expert translators, which means it's just not accessible for most of the world. Like it's just not accessible at all. You can still use that for very high stakes scenarios, like if you're like at the UN, you want to like have a very serious conversation. But like by and large, not basically everybody has access to some level of translation to communicate with people from far away places. I think what's happening is like the space of what are the jobs that are, let's say, most fun and most critical for humans to be working on will always change and evolve. That's always been true. It's happening faster now than before. And I think that creates unique challenges in how we think about continuing education and training. But by and large, I think the key consequence is now like, as a single person, you can just do so much more. And what does that mean? What kind of opportunities does this enable? I don't think that I guess I don't fear of there's always too much work to do. It's not the not the other way around. Yeah.
Yeah, I guess in my aspects, like, and I work with, well, some machine learning models and also robots, right? So sometimes people also ask like, so now the robots are doing the job, so what do you do there in the lab anymore? Actually, we are even busier than before because sometimes robots can still be done, to be honest, and they still need to be trained, right? We need to tell them what to do. And we need to sort of decide, okay, maybe this robot needs a camera, and then we need to put computer vision, a lot of things to it to make it smarter so that it can be more adaptive to different kind of things. Because sometimes experiments or doing experiments, or especially like chemical experiments, can be kind of random, have random results or different kind of outcomes, so that the robots may not be as good as human to sort of being responsive or like being adaptive to the new outcome that it may see. So we as humans still need to think about a lot of this sort of way ahead and then decide how to train the robot arm to do those jobs. So there are a lot of sort of thinking process. And now we are not just thinking for ourselves, our own performance. We also have to sort of think for the robot's performance and the AI's performance. So I think there is a lot of things there. But in the training part, and also in the like we need to keep like upgrading how good the model is and how good the robot's motion is, something like that. We are not really like satisfied at this point. So for sure, there are a lot of work to do. And beyond that, like I kept mentioning about sort of framing a question or like formulating a hypothesis, I think that's the part that AI may be like catching up, but I feel like there is a long way to go, especially when we have a specific, like very specific goal, like to make a certain material like that.
Great, thank you. So in our last minute before we wrap up, I'd like to first thank our panelists for being here today. And if you all could leave us with some words, if some students wanted to get into your pathway, most of the students that are looking right now are high school students, as well as some undergraduates and possibly some folks who are in their careers right now. What advice would you give them for getting into machine learning and AI, you know, in a 30-second quote? Yeah, and if you want to start, and then Adam, we'll have you finish.
I think the first suggestion I will have is open to opportunities and open to learn new things anytime, at any stage. And I feel like we are really in an era that we have access to so much resource, different kind of resource, especially in this AI related topic. There are a lot of resource online that is open access, free, and I feel like many people have put a lot of effort to make a great video to explain for some concepts or even how to use the model. So again, like open to these opportunities, open to this resource. Whenever you are interested in something, you can always get started with something and put some effort in it. And of course, it takes time, but you will also see the change in your own brain. Like when you put effort in something you like, that will really make a difference.
Yeah, I would say my general advice is just to continue trying. I mean, like, maybe the current environment you're in doesn't have the greatest opportunity, but it's a long game. Like you can basically like continue to reach out for opportunities, continue trying to find a place to give a chance to work harder on it. If you're not ready for it right now, there's lots of online courses. Like the most important thing really is a mindset of continuing to try and being optimistic in the face of setbacks. Because if any given try maybe has, let's say, a 5% chance of succeeding, But if you try for a year and you're trying consistently, then the chance of it working out eventually is 100%. As soon as you give up, it goes down to 0. And that's true, not just in like getting the opportunity. Like I got lucky. Like I cold emailed someone who was fantastic. They happened to get back to me. But I cold emailed a bunch of people who never got back to me. And it's true in kind of every single stage of your career. There's a lot of just inherent luck in that process. And the only thing that guarantees that it's not going to work out is when you give up and say, this is not possible. And the only thing that guarantees that it will work out is just you try long enough. You never know how long, right? Like maybe it looks like maybe 10 people didn't get back to you. But as long as you're optimistic, you're continuing to grow and working on both your skill set from whatever resources you have, you continue trying to find opportunities to actually do the work, then it's guaranteed to work out eventually, just a matter of time. So just try. Don't give up.
All right. Thank you so much for those final words and that final set of advice. Again, thank you to Adam and Yen for taking the time to talk with us today. I think the students really appreciated it. And we look forward to our next week when we're talking to our environmental scientists about their work in the field. So thank you so much, everybody in attendance, and thank you to our panelists again. And have a good long weekend, everybody.
Thank you very much.
Bye, everyone.
Bye.